This is Bob Stather, our chief engineer, and actually the designer of the power plant. And so I would think there's probably nobody on the planet that knows more about it than Bob.
We would hope.
We would hope. So what do we have here? We've got a P12, and this is our second largest power plant. And it's an AC
Third.
regenerator. Third? We have the P3.
2015. Oh,
I was going from the bottom up.
okay. Second smallest.
Second smallest. Okay. Remind me not to put them in the marketing department. So the power plant is a regenerator. It takes the AC waveform and on the hot side converts it to DC and then regenerates using a power amplifier and as fed by a sine wave generator that creates a perfect low distortion, low impedance output that will feed your equipment. So regardless of what you put into it, what you get out is kind of pure power. And one of the things that people want to know about is the output impedance, because we talk a lot about that, one of the more important things. And Bob, maybe you could, why don't you explain to us, like you and I were talking, that a very low output impedance is the same as if there was only a very short length of wire connected directly up to the city power, as opposed to miles or hundreds of feet. Kind of explain that impedance bit to us.
Sure. So at some point in the electrical system, there's a voltage that hopefully doesn't change. That anything you can do, and it doesn't care about the power plant, it puts out a certain voltage, and nothing you can do changes that. And then there's miles and miles of stuff between that and you. So in reality, when you draw more power from the wall, because of all the resistance of the wire, of the transformers, the transmission lines, everything else, the voltage will drop because of Ohm's law says that if you put current through a resistance, there's a voltage drop. And so what our power plants try to do is counter the effects of that by regenerating the power directly right there next to your stereo system.
So we're in effect regulating the power.
Exactly.
Yeah.
Yeah.
Yeah. And that is important for a number of reasons, but certainly when you're running a power amplifier, you'd like to have regulated power. Because when a big bass drum hits or something that's taking a lot of energy, the line voltage can drop and you'll have less effective power. But really, I think, and Bob, correct me if I'm wrong here, at the end of the day, that's probably not the biggest impact because, yeah, it's down a couple of volts, but you're likely to be able to put out as much power as your amp. Really, from a sonic standpoint, it makes a lot of difference in terms of the power supply noises, of how it's modulating the power supply and what the effects are. And when people hook a power plant up, what they find is this wonderful openness and it just sounds amazing. Well, I don't want to give a big pitch for it here. So we're my natural tendency is I'm going to stop it right there, and we're not going to go any further. But we're just going to have to measure this. So tell us what you're going to do to measure this, and what is it we're measuring?
Sure. So what we're trying to do is we're going to measure the resistance or the impedance of the power source. And I'm going to do two measurements. First, I'm going to measure what's coming out of my wall here on my test bench, and then we're going to connect the power plant and we're going to measure it again.
Okay.
So we have a little contraption here that we built a while back, and it's just a short piece of cable, and it's got leads that connect right at the connector. It's going to my voltmeter.
Okay.
And then it's got a loop of wire here that my current probe is on, and that's over here going to an ammeter.
Okay, so just, we'll try and do this in plain English for people. So this is showing 122.4, which is the voltage coming out of the wall.
Correct.
And this is showing 3.4 millivolts, or no, what would this equate to? This is amperage, but...
Yeah, it's showing 3.4 millivolts, but this probe is 10 millivolts for an amp.
Ah,
So that's actually 0.3 amps.
okay. So
We have to do a little bit of math.
300
to convert.
milliamps or 0.3 amps.
Right.
So we're drawing minimal amount of current.
Right. Right now, the only thing that's running is we have a test load here. This test load has 4 switches, and each one is about 300 watts. There's fans in there, and this is really the current of the fans. That's all that's on.
And these
right
are just big resistors inside, right?
just big resistors. yeah.
Okay. All right.
Lots of them.
Yeah. And they get hot, so we got fans to cool them down. Okay.
Yep.
All right.
All right. So, as you can see, right now, coming out of my wall is 122.4 volts.
Okay.
And I'm going to write that down. And that's with, very little load. Now I'm going to turn on, say, 3 of these. And you can see the voltage just dropped to 117.8.
Because we're drawing
Volts.
current, and because the wires in this building have a certain length, which makes a certain amount of resistance. So as we start drawing current, the voltage has dropped from, what was it, 122?
122.4.
And now we're down to 117, call it 118. That's because you're drawing current, as we would with a power amp or, okay.
Okay. And before, it was current, as Paul noted, was 0.3 amps. And now this is actually 7.65 amps.
Okay, so we're drawing.
So we're doing that. So now I'm going to take, how much did the voltage change when we did that?
Mhm.
It was 122.4 minus 117.8 is 4.6 volts we lost. And we went up 7.35 amps. And,
Okay.
and Ohm's law says the resistance is the voltage divided by the current. So I'm going to take 4.6 volts and divide it by 7.35 amps. And I get 0.63 ohms.
So a little bit more than half an ohm.
A little bit more than half an ohm here at my bench coming right out of the wall.
Okay, so that's, and if that was 0 ohms, then over here, when we started drawing current, then nothing would happen. It would just stay right at 122, which would be the definition of a regulated voltage.
Correct.
So in a regulated voltage, regardless of how much current you're pulling from it and how quickly you're pulling it, it just stays the same. Okay,
Okay.
so now,
So now I am going to break this connection right here.
okay,
And I will plug this into our P12. And I'll plug this into the output of the P12.
okay, and
And we will give it
Does-
a moment for this to come on.
okay. So now we're going to power from the P12, which is also plugged into the exact same line that you just had done, correct?
That's correct.
Okay,
Okay.
there we go. Now, let's see, what do we got here? So coming out of the P12, looks like we have 120 volts, and we're drawing the same 330 load, which is, so you can see over here, and we can on the P12, we could adjust it to 122 if we wanted to. But
could,
we could, but
why
for
would we want
purpose,
to?
well, yeah, why would we want to? Because it really doesn't matter. Okay,
Okay. So I'm going to turn on the same 3 resistive loads.
oh,
And we can see now the voltage dropped just a tiny bit, 119.8.
so we went from 120 to 119.8, so that's a little less than 200 millivolts. I'm not the best at math, but well,
Yeah.
Bob, is that right?
Um,
So where we dropped
300 or 400 millivolts.
300 or 400
It
millivolts.
was slightly above 120 before.
Okay,
Okay.
as opposed to multiple volts, which is what dropped when we were right at the
We
wall.
were 4.6 volts before.
Uh-huh.
So I'm going to do the same math. I'm going to take 120.2 and subtract 119.8. That gives me 0.4 volts.
So 400 millivolts or 0.4 volts.
And the current is now 7.77 amps minus 0.34 amps is 7.43 amps.
Mm-hmm.
And if I take 0.4 divided by 7.43, I get 0.054 ohms.
So 0.054 ohms compared to
0.63.
so a magnitude better
Magnitude better.
impedance.
And
Right.
this number actually includes this connector, this piece of cable.
Right.
So if you were to be a little more refined about taking this measurements, if I were to put the probe directly into the outlet, it probably would be more like 0.04.
Right.
This number, 54 milliohms, is on the order of, like, this piece of wire has more than 54 milliohms resistance
which
right
is
here.
kind of amazing, really.
Yeah.
And so what that means is by regulating the voltage like that, that we are essentially taking a piece of wire this long and connecting it directly up to the city power for our amplifiers and our preamplifiers and all that. And that's what's meant by that low impedance. And this is the proper way to measure the output impedance of a power plant. And this is how we do it. And when we do it and when we spec it, we actually do it right without all this stuff. And we get a more accurate reading, which also is a little bit lower. So another thing that power plants do, in addition to regulating the voltage, which is very important, is we maintain the quality of the sine wave. And I wonder if we could, maybe we'll flip this, maybe I'll flip the camera around and let's see what the distortion levels, how they change, and then we'll talk about that. Is that okay?
Okay.
Okay, I think I can just keep this live so people can go over here and see what we got going. All right. My fancy camera here. Let's see if I can't zoom in. Oh, that's out. Well, Paul can't operate a camera. Oh, there we go. Okay. So what do we have there?
This is a representative of the input voltage.
This is what's coming into
coming
the power?
into the power plant. You can see at the top, whoops, don't touch the screen. You can
It is a touch screen after all.
It is a touch screen, and if you touch it, it does things. You can see at the tops and the bottoms there's a little bit of flattening, and that's very common because of all the power supplies that draw power only at the peaks. It tends to flatten the top of it.
And this is actually pretty decent power as power goes. I've seen, and you and I both have seen far worse.
Far worse, yes. Right now, this is 3.2% total harmonic distortion coming in.
Okay, and by harmonic distortion, what we mean is that the shape of the wave is not perfect. If it was a perfect sine wave, you'd have 0% distortion. The more harmonics that get added to it are a function of the shape of the wave changing, and that's because of everybody pulling power right here. Oop, I didn't touch it, I'm telling you.
Time's out.
Yeah, okay. Everybody in this building and along all our neighbors, we're all pulling power at the same time, right at those peaks. And that's what's pulling down that waveform. And so now here's the output of the power plant, and you can see that has all been corrected. Notice, maybe you can point out, Bob, yeah, those nice purdy
curved
peaks.
tops, yeah.
Yep, nice purdy peaks. Those are beautiful. And so what's the distortion there?
We'll go back and forth here a couple times so you can see the difference.
There you go.
If we were to compare it, just look at the difference. We've got a thing here, and this shows you what the difference between those two is, and there's some amount of distortion in these big humps, and then you can also see a lot of fuzz on there, which is higher order distortion and noise that's being removed from the signal.
So that's what's being pulled out of the signal that we don't want.
Yep.
Yep, okay.
And so right now we're putting out 0.1% distortion.
Dang, that's pretty, so 0.1% distortion. And one of the reasons we built on every power plant, here's my marketing pitch. Um, One of the reasons we built this to show people is because we used to get a lot of grief from competitors who go, oh, ours does this, ours does that, ours lowers distortion, ours regulates the voltage, and literally none of them did and do. The power plants are one of the few out there that actually do regulate, lower distortion, give you a perfect sine wave. And so we thought, we can talk to her blue in the face, but at the end of the day, this says it all. It shows us. Would it be possible to talk a little bit about why that might be important?
These are flattened because most pieces of equipment draw power right at that peak of the waveform. So the unfortunate consequence of this is that this is being lowered right where you need it the most, right where, this is driving me crazy, right where you need it the most is where it gives in. And that's just a symptom of the way people have been designing power supplies since the rectifier was invented. I don't know when that was. And PS Audio is partly guilty too. We design our linear supplies in most of our products, and they also draw power right at those peaks.
Yep.
And
they have a power factor that we say is lower than 1. So
right.
and maybe you could explain that. I try in my best to explain to people. Maybe you could. What does that actually mean?
So power factor is the difference between the way that a certain piece of equipment draws power from the wall compared to what would be ideal. And that the power company would love it if everything in the world was just resistors and light bulbs, and they all draw a current that looks exactly like the voltage and makes their life so much easier. In the real world, there are motors that draw current that's not in phase with the voltage, to where when the voltage is at its peak, the current is not at its peak. The current's at its peak when the voltage is lower. That's a problem. And then also things that draw current that are not sine waves, not in the same shape as the incoming voltage. So all those things combined create a condition where the amount of current that you're getting is greater than what would be optimum. So where if it were a perfect sine wave, maybe something would need 1 amp. 1 amp at 120 volts would be 120 watts. But because it doesn't draw the current in sync with the voltage, that 1 amp is only giving you 60 watts, 80 watts, some lesser number. And the ratio between that is called the power factor. So if my 1 amp is only giving me 60 watts instead of 120 watts, that's a power factor of 0.5, 1/2. Means that I'm only getting half of the power from my 1 amp that ideally I could.
Lastly, if you wouldn't mind, could we talk a little bit about multi-wave? Multi-wave is one of the features of the power plant, and we add a little bit of third harmonic to extend that peak up there. And why would we do that?
Okay. Well, we've already kind of given you the reasons for that, in that, like we said, most pieces of equipment only draw current at this peak. So, a long time ago, we came up with the idea is, what if we could make that peak wider so that there's more time for the capacitors in a power supply to charge? And we came up with multi-wave, and let me just turn that on here. I'll turn on multi-wave, and then go back to the scope. And
There.
And maybe if you remembered what it looked like before, it was a very sharp peak. Now it's rounded off a little bit more. So by adding third harmonic of the 60 or 50 hertz, we round off this top a little bit, and now it's got a wider pulse, or a wider amount of longer amount of time that the power supply can deliver power into the capacitors. And so what that does is if I deliver half the current for twice the time, same amount of power goes into the power supply. Power supply's happy. But all the losses in a piece of equipment, the resistance of the transformer and things like that, especially the transformer is probably the biggest impedance in between your power supply capacitors and the wall. Losses, according to Ohm's law, are I squared R, or the current squared times the resistance. So if I can cut that current in half, I cut the power dissipated by 1/4. So now but I still have to make it twice as long. Mm-hmm. So I've really only cut the power dissipated in half, but half, that's pretty good, right? That's the inside your power supply and your power amplifier or whatever, the transformer is only getting half as hot as it would have with a pure sine wave.
When we originally thought of this idea, like, since we can't do anything to the internals of your amplifier or your preamplifier. You don't want us in there, we don't want to get in there. So what could we do externally to try and make an improvement to your product? Well, we know that bigger power supplies in general sound better, whether it's a preamp or a power amp, and the bigger they are, the better your equipment is going to sound. But there's only so much you can put into a box. But by changing the waveform, regulating the voltage, extending the charging time, we have effectively given you a bigger power supply, and that's one of the reasons why we can give you better sound. Does that sum it up reasonably well?
Yeah, it sure does. Yeah, we can't, the power capacitors in your power supply have to take all the energy in that short period of time and save up enough to deliver power to your amplifier the rest of the time. Mm-hmm. And so we can't do anything about the back end. We can't change how much power your circuit wants to draw. But what we can do is say, well, we're going to give you more time to charge. We can't give you less time to take it away, but we can give you more time to charge. And so there's a benefit there that you're able to get more, recharge the energy in the capacitor more efficiently.
Yep. Okay. Well, Bob, thank you very much.
You're welcome.
We greatly appreciate your time and showing us the P12, how it works. And, you know, it probably would be helpful in the future to do a few more of these videos just to make sure everybody gets the right story.
Okay.
Okay.
No problem.
Thank you, sir. Bye.
Thanks for watching.